we're gonna do an angle beam profile and you're gonna like it. When I say beam profile, I mean the vertical beam profile. This is the classic one that you'll do in your UT training, and then you may never do it again after you write your exam. Now, we know some of the basic things that produce beam spread. The smaller the transducer, the more the beam spread. I call that one the sawed-off shotgun analogy. The lower the frequency, the more the beam spread. That's the my neighbor has 12-inch subs in the car and listens to dance music analogy. We know these things. We take them into account when we pick a transducer for a job. You may never actually do a beam spread on a job. I've done it once, but it's good practice. We'll follow the procedure in ISO 12715. This is pretty much the same as ASTM E164. For the block, I'm going to use an IOW beam profile block, probably similar to the one you're going to see in your course. It's got side drilled holes. They're spaced nicely far apart, which gives us lots of sound path length, and we can get into the far field. The IOW block is 50 millimeters wide. It's got 2 holes on this side, 2 holes on that side. We can hit each of them from the top of the block and the bottom. That gives us 8 possible targets. Grab your favorite flavor of masking tape. Mine is mint. Put a piece of tape here and a piece of tape here on the top and bottom of the block. You can do the other side if you're also going to use those holes. And mark the position of the holes. One of them was hidden behind the tape, so I had to poke a little hole. And this hole is 19 millimeters from this surface. The height of the block is 75, which means that this distance from this surface to the hole is 56. And I did the same thing on the other side. Another little trick, this block is 50 millimeters high. This AWS resolution block is 25 millimeters high, exactly half. I'm going to place this on this side of the block so I've got something to ride my probe on. We'll be filling out a table like this with distances and depths. The Y is the depth. Those are the depths of the holes. We already know that. That's the design of the block. And the distances is the surface position of the transducer on the block. I'll be using this 2¼ meg transducer on a 60-degree wedge. And before we get started, we did do a beam index point. It's right in the middle. The first hole is at a depth of 19 millimeters. We're going to move the transducer back and forth until we peak the beam right about there. And then we're going to mark the center of the beam right here with a long line. Then what I'm going to do is add 6 dB, pull the transducer back until that signal comes back down to my reference line right here. Again, mark the position of that line. This time I'm going to do it with a short line, and then you're going to do the same thing on the other side. It's going to go back over across the top and down right there, and then we'll put another short line right there. This position represents the bottom of the beam, and that position back here represents the top of the beam. We then do the same thing for all the other holes. We peak this signal right here. We're going to mark a long line, add 6 decibels, move it back, mark that spot, move it the other way, mark that spot, and do the rest. We've got C for center, B for bottom of the beam, and T for top of the beam, and we're measuring the length from here to here for each one. On the graph, you get a visual of the beam angle and the beam spread. And if you want to mathematically solve for exactly what those numbers are, you could use like an inverse tan or arctan function in Excel, distance over depth, or you could just use a protractor.
Too bad we don't live on a farm.
When we infer a point beyond our data set, we call that extrapolating. And we can extrapolate the center line of the beam back to the origin of the graph, or 0, 0, pretty safely. That's the beam index point. But we can't do that with the edges of the beam. The beam has some width coming out of the bottom of the probe, so it can't come to a point. As well, if you want to draw a straight line between data points instead of just playing connect the dots, that's fine too. But do that only on the points in the far field. Points just below the surface, maybe in the near zone, and the near zone tends to be a little bit wonky. I chose a 2¼ meg transducer over a 5 just because it's a lower frequency, a little bit more beam spread, a little something more to look at. When we plot the 45-degree wedge and the 70-degree wedge, just look at how much the beam spread changes over angle. So even though it's the same size of transducer, and all we did was change the incidence angle at the top, that's due to something called effective aperture. That effective aperture drops at 70 degrees. That's why it gets so wide and messy. I'm going to talk about effective aperture on another video. Beam plots. We should know how to do them at least once in our careers. I hope you enjoyed the video. If you did, please hit the like and subscribe buttons, and thanks for watching.